Hello again. Tonight we're going to talk about maybe thinking how optical SETI does its investigation and maybe suggest some alternative approaches to it. So, for those that aren't familiar with it, SETI is the Search for Extraterrestrial Intelligence. It's actually Extraterrestrial Intelligence Institute, so it's actually the SETI Institute. It's a private concern. They initially had government money, but now they're on private funding. They were renting time on existing radio telescopes, and they got some funding and created their own sets of radio telescopes and some other radio observatories. They still get data from them, but it's basically to observe longstanding in radio various wavelengths, frequencies, such to conclusively record indications of intelligence elsewhere in the Milky Way galaxy. But they've been spending a couple of decades doing this, and nothing conclusive as of yet, either saying they definitely found something or concluding that they're going to give up because they haven't found anything. Originally, it was in radio, and then they moved into optical, which it's not really just optical. It's more like they're looking for modulated light beams or lasers, which is what we're going to focus on. But they've also added new flavors, which is astrobiology and astroarchaeology, so that if they do detect something, they'll have some people that are experienced in those disciplines to further investigate. Information we're getting back these days regarding spectral analysis of light that passes from a star through an exoplanet's atmosphere, and then we pick it up on Earth, and then we can analyze what chemicals are in it. That's a good way of looking at the signatures for biologic life, but it doesn't really tell you about the technology. So radio SETI has been kind of looking in the electromagnetic spectrum at what you would think of as human analogs of communication. So they would be looking for the same kinds of modulations of radio emissions that we do here on Earth. And another one, which is the quiet hydrogen zone at 21 centimeters. And if somebody's from elsewhere and they're sending at 21 centimeters, it's quiet there. So it would have to be purposed, deliberate transmissions in that particular wavelength. These are the kind of emissions that humans on planet Earth have been doing for roughly 100 years ago until today. And we use it still today for open space communication of voice, video, and data. But at one time, humans used smoke signals, and then they found out it was much more effective and efficient to use modulation of the electromagnetic spectrum, basically switching on and off streams of photons or fluxes of photons. So maybe extraterrestrial intelligence will be using the electromagnetic spectrum for communication. But much like we moved away from smoke signals because they just weren't good enough, we've said, well, when we go out to other places in our solar system, we establish bases. Instead of using radio, we're going to use lasers because higher bandwidth, more reliable communication. So SETI looking at laser is kind of a next step thought. But even farther than that is the electromagnetic spectrum has a number of issues for use in deep space communication. But as we found out recently, gravity waves come in all sorts of wavelengths, frequencies, and there's good evidence that there's a cosmic background gravitational wave that's been around a long time. And so if we can ever learn to decode or demodulate that and encode or modulate that, we may find that for the same reason that we gave up smoke signals and went with the EM spectrum, more futuristic societies out there in the universe switch from modulating the electromagnetic spectrum to modulating gravity waves. But we'll leave that aside for a moment. Let's get back to optical SETI. So the reason for adding in optical SETI is that we're now thinking about doing the same sort of thing, using lasers for communication from the Earth to bases on the moon, because the same side of the moon faces us all the time. We need multiple laser transmitters and receivers on Earth, but you'd only need like one side of the moon. As we get to the outer planets and their moons, lasers could be useful there too for higher bandwidth, more reliable communications. And Once you go out even further, same sort of thing. And once you establish, let's say, a base on one moon of Jupiter and you want to talk to a moon of Saturn, they're a lot closer, only a few 100 million miles away. And lasers would work well there too. So moving from radio SETI into optical SETI, they're still doing the radio bits, but adding in optical SETI makes sense. But they're making some presumptions about the SETI observing that they've done at this point, is that they're assuming that intelligent life out there is going to be modulating the electromagnetic spectrum, not using gravity waves, and that they'll have lots of transmitters, kind of like we do here on Earth. Everything is transmitting in all sorts of frequencies. We've got Bluetooth and Wi-Fi and long-range microwave, and all those things are transmitting. And the communication that are always on, they always have a carrier signal. That's the baseband signal that gets switched on and off or modulated, and you can detect the carrier. We found that that's a waste of energy. Why leave the carrier on when you're communicating point to point? Why not just turn the carrier on shortly before you start transmitting and turn it off when you're done transmitting, saving lots of power? Otherwise, it's just idle consumption of power. Now, if you're looking for things out in the universe to always have their carrier on, why would they? We don't. And we've gotten even further. The actual communications is burst-based. And you might have heard of this in covert work, where they're using burst transmitters. That's instead of in real time communicating, like, let's say I'm speaking in real time and my voice is getting modulated like a voice over IP telephone communication connection. Instead, I would say what I wanted to say one way, package it up as highly compressed, and then when I went to send it, instead of 30 seconds worth of dialogue taking 30 seconds, 30 seconds of dialogue might take a small fraction of a second. So in covert work, that's a burst transmitter. You want to send pictures, send them compressed, send them resolution reduced. They take far less time to send and burst transmit. As we've started to have higher and higher communications demands, we want improved signal to noise ratio and better use of power resources. Our own transmissions on Earth have become focused, not just a wideband omnidirectional, but actually narrow beam and bursty. There are forms of communication that are in all directions and are what is known as leaky. Some of the stuff that gets sent, the photons that get transmitted, aren't intended for anyone else. They're just intended for the receiver, but they're kind of like you drive down the highway and you look at the street lamps. And the street lamps are meant to shine straight down onto the highway, but you can see that street light from like a mile and a half away, which means photons are at an odd angle getting all the way down the highway. And so that's the same sort of thing in radio, that if it's a very directional radio signal, not much on the side gets out, not much of it's leaky. But if you don't really care and you've got enough power, then make it a wide angle and you don't have to point your antenna so precisely. But that's just how things are going through. Then you have to pick the particular wavelength to make sure that whatever signal they sent was of the right energy level to get through their atmosphere. And once it arrives towards Earth, it has to get through Earth's atmosphere. Some frequencies don't pass through the moisture in the Earth's atmosphere or ionization in the Earth's atmosphere. They're counting on things being just so in order to improve their odds of being able to receive. So here's kind of what I think might be wrong with optical SETI. First off, there's nothing wrong with optical SETI. There's just some things that maybe they haven't considered. Lasers, being a narrow beam, are tightly focused. So if a laser is pointing from one mountaintop to another mountaintop, the amount of beam that would be leaky and leave that planet and come to Earth is fairly limited. If there is a laser out there pointed directly at Earth, yeah, that has a higher probability, but we have to get into positional stuff. But the beam itself may be switched on and off. It may be in or out of phase. And if you're trying to receive something when it's switched off or in the wrong frequency, it'll be sending, but from your perspective, it will be undetectable. But also think of it as if I'm wanting to send a laser beam from some extraterrestrial planet to Earth because I've spotted where Earth is in the galaxy, the Earth rotates on its axis every 24 hours. where is our receiver for that laser? The Earth is in orbit around the sun, and the sun is in orbit around the Milky Way. So if you're sending from someplace else in the galaxy, you have to line everything up just right. And since light doesn't travel instantaneously across light years of distance, you may want to adjust where your beam is pointed to communicate with Earth, because if you just point it at Earth, you're pointing at where Earth was when the photons left it and got to your telescope, and that's where you picked up Earth from. Earth is going to be somewhere far different and facing the other direction. The other thing is they've been using photometers for detecting extraterrestrial laser pulses. And photometers are the kinds of things that are used to judge the brightness of stars, the color of stars. You can think of them as single pixel cameras or single pixel imagers. If that laser were being modulated at a certain frequency, then you've got to sample at twice that frequency in order to pick up the modulated signal. So if the photometer is being given, let's say, a 30-second exposure duration, and the modulation we're trying to pick up is a small fraction of a second, it'll just look like a light. You won't actually see the modulated data. The second thing is, if you're pointing your photometer at a star in the hopes of getting data from an exoplanet around that star, if the planet is orbiting that star, then when it goes behind the star, from our perspective, it can't send us anything. And if it rotates on its axis like the Earth does, maybe not in 24 hours, maybe a different number, but if it rotates on its axis, they have to wait until the beam can be pointed towards Earth, or where Earth will be when those photons cross the multiple light years distance. If you're pointing your photometer at a star, stars put out their own wavelengths of random light fluctuations, broad spectrum fluxes of non-phase aligned or non-coherent photons from things like solar flares and coronal mass ejections. And so if you're attempting to pick up a laser modulated pulse amongst all that other random photon emissions, good luck. You'll probably be blinded by the spectral brilliance of the star. So as somebody once said, "You're so smarty pants. What do you want to do? What is your suggestion?" Well, my suggestions for improving things would be stop focusing on the intentional and start focusing on the incidental or unintended emissions, not the purposed stuff. On Earth, we're always complaining when we're doing radio astronomy about electromagnetic interference or radio frequency interference. That's EMI and RFI. That's just the hash of everyday existence of electronics on this planet. Well, there's a lot of that, and we're increasing the amount of that, but it's not intended as communication. It's just noise, background noise. If we don't like light pollution, then radio pollution is the same sort of thing. But if we're attempting to detect whether or not an exoplanet around a star, a distant star in our galaxy, has technology, look for the EMI and the RFI. Look for the ever-present stuff, the stuff that leaks out into space, can pass through both their atmosphere and ours, and would not be produced by nature because it's junk noise in radio or laser on a continuous basis. The most obvious one is power grids. We just take it for granted. Power grids produce their own radio frequency output called very low frequency, and that's your 50 and 60 hertz cycling of the power, because the power is generated by motor generators and they spin, and you have, commutators and armatures, and you can't produce an alternating current phase-free voltage. But don't look for normal 120 or 220 volt amplitudes. Look for the big stuff. Look for the 100,000 plus volt grid lines, because they're also pumping it out at 50 and 60 hertz, right up until they use superconducting and they embed them in the ground, and they're now running extremely high voltage DC, which would not produce this emission. But ever since we started powering things with alternating current, we've been leaking 50 and 60 hertz, very high amplitude collective emissions. Don't presume that all those emissions are in phase. The peaks and troughs of the 50 and 60 hertz from all the generators in a city will be slightly out of phase with one another because they're different motors running at just slightly different RPM alignments to their generator output, their commutators. Just look for the random hum of things in the VLF frequency range. And the next one's a relatively new one, which is pulse wave modulation of mass deployment of light emitting diodes, LEDs. When they first started using LEDs, they would just be, if it's on, it's on. And they found out that wastes a lot of power. Human beings have a limitation on how fast they can see it blinking on and off. So they started, even the lights, their light bulbs, your LED light bulbs in your house, they're not continuously on. When they're on, they're actually turning on and off at about 1.2 thousand times a second. You just don't see it. If you look out of the corner of your eye, you might notice a little flickering, and that's what this is. It's meant to save power. That's how you go from a 60-watt incandescent bulb to maybe an 8-watt LED bulb down to a 4-watt LED bulb. It's because it's not always on, even when it's on. So if you're going to use a photometer to detect this, your photometer needs to have very short sample durations, probably twice 1.2 kilohertz in order to detect the 1.2 kilohertz. The 1.2 is just what us silly humans use. Elsewhere, they could be using a higher frequency because the physiology of their eyes are different, or they could be using a lower frequency because the physiology of their eyes are different. And lastly, you need to get away from the Earth-based EMI and RFI, so put your radio and laser listening off-world, backside of the moon when the moon is not new. In other words, when the moon is not under full solar illumination is probably the best way to do it. So in summary, long-term, SETI should consider gravity wave modulation communication. Start with receiving, don't worry about transmitting. Second is the Milky Way and the universe are extremely big places. Don't get disheartened because we haven't heard anything yet, especially since we've still got improvements we can do in the process that we're using to look and listen for things. Everything's moving in the universe. So if things don't line up, that's probably the reason why you're not picking anything up. The perfect alignment at the right time, odds are slim. Keep your sampling not continuous, but brief at the right time. And optical SETI should be looking for very low frequency, unintentional power grid emissions and mass deployed illuminated lighting off-world. And as someone who believes in the zoo hypothesis, the Drake equation, I'm not disheartened by the Fermi Paradox. I think it changed over time, given that we went from having maybe 1 million stars in the Milky Way to now the number is approaching 400 million, which gives much better odds for the Drake equation. The Fermi Paradox kind of falls by the wayside when you look at all the difficulties of trying to detect something outside the Earth. And then the zoo hypothesis says, orange and red stars have been around for maybe 1 billion years longer than our sun, and therefore extraterrestrials might have at least a few 100 million years head start on us as far as technology goes. And so they may be out at the outer edge of our solar system where we're looking for, planet 9, planet 10. That's where they've got their observation station, and they're keeping a arm's length watchful eye over what the animalistic and aggressive human species does. So look for the unintentional stuff, the always on, the leaky stuff at the right frequencies, and don't look so much for the complex modulations of data. For SETI, I hope it all works out. Let me know if they find ET. And if they do, and this helped, you're welcome. If not, why are you listening to some random person on the internet? And then if you want to know about all those various things, as usual, there'll be links. Okay, I thought that would be a good change of pace. Any comments or questions?
I was wondering as you were speaking, the laser that is shot up from the hard rock, does that penetrate our atmosphere out into space?
I believe it does, yeah.
Seems like it's pretty powerful.
Yes.
Yeah.
It's not just the power, it's the particular wavelength.
Yeah.
Given that it's very bright, detectable colors as well as white light, I think it probably has enough energy, enough flux to pass through the atmosphere to space. Now, remember, we may think of it as a tightly concentrated beam, but by the time it gets dispersed by the Earth's atmosphere, if you said, I want to see it from the moon's perspective, it would probably be a couple of miles across
Yeah.
diameter. So that
Yeah.
high power beam, that flux would be very widely dispersed. And imagine if you were using a megawatt laser that was extremely tightly focused and you sent it out, let's say 20 light years out into space. It would cover at least a planet, if not a good portion of a star by the time it got anywhere.
That was my next thought. I was wondering how far out you would have to be so that a laser pointed at us would be wide enough to, let's say, cover our entire orbit around the sun.
Oh, probably. Well, it depends upon the power and the flux and the concentration of it. But I would say if you wanted to cover the planet, probably a dozen or so light years. If you want to cover the width of our orbit around the sun, maybe 50 or so light years.
Mm.
But the photon density would rapidly tail off.
Yes.
The beam gets more and more dispersed. So if you initially were sending out a gigawatt, by the time it spread out over the diameter of the Earth's orbit around the sun, it would be a very tiny fraction of 1 watt.
Yeah.
So look for the stuff that's not intended to be sent, that is ubiquitous, always on, and has a
Always.
very collectively high output. And that would be the power grid or illumination of all the modulated LEDs from planet Earth.
Yeah.
There's no data in it, but it sure is an indicator of technology. Maybe not
Yeah.
intelligent life, but technology. And we'll start there.
So the radio waves from our power grid penetrate the atmosphere and go into space. Wow.
Yep.
Hmm.
Remember the gravitational waves that we've detected recently are very low frequency and they travel multiple light years distance. So our power grid at 50 to 60 hertz, it emanates so strongly that if you're connecting up old style audio cables in your house, when you are using a stereo plug, if you plug it in halfway, you'll get that like horrible tone. That's power grid. Now,
really? Wow.
Yes, that's the AC power grid. It is everywhere. It is very high in amplitude. But yeah, I've actually now if you want to be able to detect, this is weird. If you want to be able to detect 60 cycle hum as a very low frequency radio, all you need to do is get yourself a small AC transformer like this, and hook up one side, hook up the secondary as if it's the antenna input on your software defined radio receiver, and then tune it to about 60 hertz, not kilohertz, hertz, 60 times a second. And there will be an extremely high amplitude hum. And that's just stuff that's there all the time and nobody gives it a second thought. But if we are, powering our world with electricity, some places on the planet are 50 hertz, some places are 60 hertz. And even if you're in a 60 hertz area, different power generation stations might be running slightly out of phase with one another. So don't look precisely for 60 hertz. Look for anything that is massive as just a fuzz in the low frequency range. And that would be something nature would not have the energy amplitude to produce. Look for the incidental stuff.
Very interesting. I hope we detect something and confirm it in my lifetime. That would be fascinating.
Yes, for some people on the planet, it will be life altering. Just the fact that they've just confirmed that there is technological intelligence beyond this planet.
Yeah.
Who confirmed that?
They haven't confirmed it yet. They haven't confirmed that it's on this planet yet.
Oh, yeah. Not much intelligence here, I can tell you that.
Yeah, yeah. Well, it varies from person to person. It's a big gray area.
Yeah, well, my
I always
great
like to think of my members as being the higher tier. Okay, any other comments or questions before I stop recording? Hearing nothing.